Welcome everyone to the week 12 tutorial session of Algebraic Combinatorics 2023. I am Rati Ludhani, a PMRF PhD student at Department of Mathematics, IIT Bombay. Today we'll discuss sample questions related to week 12 lecture notes, and let's begin. Let A is equal to this matrix, then find dual of RSK of A. So last time we discussed how to get RSK of a matrix. So
RSK means first we find bivector, and
yeah,
using this we find P is a inset and Q is a recording.
yeah, exactly. Insertion one and the recorded one. So we will need to we'll first get the bivector and we calculate that. So we'll get two semi standard Young tableau corresponding to A. So that was RSK. Okay, these are semi standard Young tableau of same size, of same shape. Yeah, right, of same shape. Okay, so now we need to find out the dual of that, like dual of RSK, which is somewhat similar, but yeah, but it's different in some sense. So let's see how to get that. Okay, so okay, I think I can discuss this question first because uh, from this you will remember what was RSK, and then we can discuss what is dual of RSK. So let's try this question first. Is that okay?
Yes, ma'am.
Okay, so we have this. This is the matrix. Now, how to find RSK? So, firstly, as you said, we will find the bivector or byword. Both are the words for this. So, so what exactly this does? So you consider the position. So it's like 1 is 1 1. So you have this. So what you will write, the where it is non-zero, we will consider that position and write the row number and so this is row number and this is column number. Okay, we write that and we will repeat it as much times as the number is written. So this could be z plus, but when we calculate the dual, we only consider 0 1 matrix. So that is a difference when we consider dual RSK. So right now we are just looking at ones and zeros. So we just need to repeat it as much times. Like we just need either I have to write it or we will not write it. So it's just one times. Okay, so this entry one says you will just repeat it only one time. So it's just write for once. Now next is 0. This is 0. This is 0. So you have this next is this entry, which is row number is 2 and the column number is 2, right? So this is non-zero and we will repeat it once because the number is 1. Now next one is 1. So this is second row and third column. So this is this. Okay, so yeah, so there are not much entries in this. uh, Actually better I'll modify this question because it's so simple, because these are just in increasing order, so you will not really need to uh, bump something. So you will bump something out and you put something there, so that is not going to happen because 1 2 3 are just in increasing order, so strictly increasing order, so this is not going to affect anything. So let's modify it. Okay, so what I am going to do, it's just weird, but what I'm thinking to do is let's put 1 everywhere, because it doesn't matter, we are just here to learn how to find the matrices. So let's do this. Okay, so what I'm doing, I'll just put ones everywhere. Yeah, now you have, or if you want, we can just do 0 here, just to make the sense of, like, we will not write 0, there will be no entry corresponding to 0. So yeah, this is better, I think. Okay, let's see what is going to happen with this much information. So again, what will be the bivector? Can you tell me? First entry,
1
1 1.
1
Yeah,
1 1 1 3
1 3.
2 1 2
Hmm.
2 2 3.
Exactly. So this is your matrix. Yeah, nice. So let's try with this vector. Okay. So first let's calculate what is RSK of A. Okay. For that, what we need to do, insertion tableau, and the other side you will consider recording tableau. Okay, so recording tableau will record the row numbers, and insertion tableau will consider the column numbers. Okay, so let's begin. So you have 1 here, so you consider 1, and then or you may start with 5 if you want, and now you insert 1, then corresponding to that you have in the recording tableau the row number is 1. Now next you insert 3. So when you insert 3, you will get 1 3. So that's nothing, we need to do anything. So corresponding to 3, we have the row number to be 1. Okay. Now next is 1. So now when you need to insert 1, what you will do? You will we are in RSK thing. So what we usually do, we search for AI which is bigger than this number, exactly greater than this P which we are inserting. Sorry, this A we are inserting. So 1, so 3 will be bumped out, and you will get 1, and then in the first row it is done. It will go to second row and there is nothing, so you will just keep 3. Is that clear?
Yes, ma'am.
Okay, now what you will get corresponding to this, so this is something like this. Yeah, here what will you get? So new box has been added here at this place, so you will get 1 from
1
this
1 2
2.
2.
Right, so we are done with this one also. Yeah, let's do this scrolling vertical. Yeah, so now you have this. Now next one is, you have now what will you insert? You will insert, next number is 2, so you will insert 2. So let's see what happens when we insert 2. So 1 1 is exactly, so you are looking only for the bigger number than 2. So in the first row there is like 1 1 is lower than 2, so we will just keep 2 here, there is no issue. So you will get, the new box will be here, so you'll get 1 1 2 from the earlier part, and corresponding to this 2 you got corresponding to, so you get here 2 here. Okay, after this, what uh, what what we need to insert? We need to insert 3, right? So this 3, so this is 1 1 2, and now you can see 3 is bigger, so you will just insert it here, and this is 3. So corresponding to that, what will you get? Actually this is again not a good example, but okay. So this is 2, this is 2, it's fine. We'll anyway discuss with other questions. So this is RSK of A. So so you have this to be P, this to be Q. So this is P, this is Q, right? If you want to keep it in a box, we can do that. This and this. Okay, so this is your P and Q. So insertion table is ready and recording table is ready, there's no issue. So RSK of A is P comma Q, where P is 1 1 2 3 3 and Q is 1 1 1 2 2. So note that the type will be same, the shape is same. Shape is both of these have the same shape, which is 4 1, right? 4 in the first row, one entry in the second row. So shape is same always. Okay, that's the that is one observation with RSK. Now let's see what happens with dual of RSK when you need to calculate this. Now what will happen here, what do you have, right, you have yeah, A is this, so I'll just copy this part. Yeah. So this is paste, right. Now yeah, just remove these as we have not considered yet for dual. Yeah. So now what do we have? Row number is this. Now we again need to calculate P and Q, but that will not be exactly what we do for RSK. So let's just try to write everything what we need, like the dual, in the sense that there is one modification when we try to insert a number. So let's see what happens. So firstly, again you are doing insertion tableau. This is not P right now, just recording thing. Even this is not SSYT. So okay, let's keep it here. Now what you need to do, first you insert, so again you have 5 5. Now you insert 1, you have inserted 1, so you get 1, and corresponding to that row number is 1. That's okay. Now next thing is you will insert 3, this is 3, you'll get 1, and then next is 3. So right now, so the only difference is when you consider dual of RSK, you search for AI which is either equal to or greater than A. So if you will consider a leftmost AI such that A is less than or equal to AI. Okay, so you will search for leftmost one. And the one thing, the difference is when we consider RSK, you just consider A is less than AI. That's the major difference. You are not looking at the equal to condition. So right now let's see what happens. So this is the difference. You will search for AI, search for AI such that A is less than or equal to AI, and you consider the leftmost one. So you will get 1, you insert 3. So right now in the tableau you just have 1. So 1 is definitely 1 is less than, so you are inserting 3. AI is this, so this is your AI, and A you are inserting, that is 3. So you insert 3, which will not affect because A is strictly greater than AI. So you will just keep 3. Okay, if this condition does not hold, you will insert it in the row, right? So you'll get 1 3, and now corresponding to that you get 1 1. So it's right now this is same as we did in the RSK thing. Let's see the next one. So you're inserting 1. So you have 1 3. Now you insert now you insert 1. Okay, so when you are inserting 1, now what you need to do, now the condition says you consider the leftmost AI such that A is less than or equal to AI. So earlier what we did, we just bumped out 3, and right, yeah, we bumped out 3 here. Yeah, this one. So we bumped out 3 and considered 3 in the second row and did the insertion thing. Now what you need to do, now the condition says you will bump that AI such that A is less than or equal to AI, and the leftmost AI you will consider in that case. So the 1 is here and 3 is here, so the AI which you will consider is this one, right? because you are considering the case that A is equal to AI also. Like there is a possibility if AI is if you have something which is equal to AI, you will bump that one. Okay, so what will happen at this place, when you insert one, you will bump this one out. So you are inserting, so this is new one, this is new one. New one means the number you inserted. Now in the in the next row you have to insert, in the next row you will insert 1. So first row is done. Now the number is of second row, so you will insert 1 here, because there is nothing to compare, you will just insert there. Is that clear? How did you got
Yes, ma'am. Yes, ma'am.
okay, great. Yeah, so this is the new one. Okay, now again, what extra box you have added, corresponding to that you write the row number. So that is, this is the extra box. Extra box is always the last one, wherever the last, in the end, the insertion happened. So 1 1, and here you will get, this is 2, so you'll get 2. So here there is the major difference. So dual had bumped out 1 rather than 3 at this position. Okay, okay, so yeah, this is this. Now let's see the next one. So now you will insert 2, the number is of 2. So when you insert 2, what will you get? 1 is there. So in the first row you will again look for so A is right now 2, so you will look for AI such that AI is greater than or equal to 2, so that is 3 right now. So you will bump 3 out, and it will move to the next row. So this is 1 already, and there is nothing to compare, like AI is now 3, so 2 is sorry, so I should write AM, because in every row it is going to change. So yeah, 2 has been inserted in first row. Now 3 has been bumped out, so it will go to the second row, and there you can see this will just give 3, because 1 is less than 3, strictly less than 3. So new box is here, so you'll get 1 1 2, and at the position 3, so yeah, we inserted 2 now, so this is 2. Till now is it clear?
Yes, ma'am.
Okay, great. So
Either
yeah.
either ma'am, we insert 1 na.
Mhm.
So less than or equal to 1 is possible. 3 also possible. We will give either 1. We pumped out.
So in which step? This step or this step?
Not before 1 insert 1. 1 3 after we insert 1.
Yeah,
Less
yeah,
than or
yeah.
equal to AI. 1 is equal to and 3 is greater than. Both we can.
Yeah.
We
Yes.
have 2 choices. We can take either 1 or 3.
Yeah, exactly. So we don't have choices, but the point is, in we will bump out the that AI which is either greater than or equal to A, and we will consider the leftmost in that sense. Leftmost means we are considering the smallest AI, the first. So
Okay.
yeah, A is less than or equal to AI, and we consider the smallest I.
Okay,
Smallest I
ma'am.
means you are starting from
1.
here. Yeah, and yeah, the first number, which the first AI, which is a, for which the condition is satisfied, that A is less than or equal to AI. So for example, if you
Okay.
had 113, for example, and you wanted, or you might have this, and you want to insert 1, so you will start from here. You start from the left side. So this is your A1, A2, A3. So so first I, such that 1 is less than or equal to AI. So this is your this number, right? So you will
Yes,
bump
ma'am.
1 out, and you put the new one. So let's write it with green. So this is your new, and then you will insert it in the second row, and then you can see 2 is the first one, which is less than or equal to 1. So you will get 1 here, and this will bumped out, and this will go to the next one. So you will get this.
Okay.
And when you do RSK thing, what you will do, so in the same condition, this is
Max.
dual. And
Maximum only we see.
yeah, so
A
we
less
will
than AI. 3 we
so
can
three,
bump it out.
yeah, three we can bump out. So you will get one here, and the next step three will
Mm.
go. It will just be here. Otherwise,
Mm.
if this line will be of dual, then three has to be pumped out,
Mm.
and three will move to the next one.
Mm.
So yeah, that's the major difference. Is that clear?
Yes, ma'am.
We will do more examples on this because there are more questions I will discuss on this just to
Okay.
understand. So yeah, till now
Mm.
is this fine? So now,
Yes, ma'am.
okay. So now you need to insert 3. So let's see. When you again so you need to insert 3, then you have, so in the first row you can see you will search for AI such that A is less than AI, which is not there because 1 2 are strictly less than 3. So condition is not satisfied, so we will just put 3 to the next. Is that clear how 3 has been inserted?
Yes, ma'am. Yes, ma'am.
So this is the
There is
same
no
thing.
element greater than
Yeah, so
comparing to 3.
so there is no element, so we will just insert an extra box and we will write that number in that box. And corresponding to that, the recording has 2, so this will be 2.
1, 2.
Yeah. So this is your insertion tableau. I should not say insertion. So you have this and this. This is recording one. This is insertion one. But if you observe, this is not semi simple. Semi standard Young tableau, because it says that over the rows it should be weakly increasing, and over the columns it should be strictly increasing. And you can see one and one are same, like over the column it is weakly,
Column. Mm.
yeah, it is
Mm.
equal, so that means it cannot be
Column
strictly.
is
Hmm.
row is strictly increasing.
Ha.
Here is Q is
Hmm.
semi-standard tabular and
Yeah.
P is not semi-standard.
Q is semi-standard, but not this.
Mm.
Not this.
Uh,
So what we consider, so as you have observed that over the rows it is strictly increasing. So we will just take the transpose of that. So we will
mm.
take P dash, which is transpose. So the new one we will call it P. So we will, the transpose of this is 1. So we'll take 1
1,
1
2, 3.
2 3
Mm.
and 3,
1, 3.
right?
Mm.
Okay, this is
Mm.
so you got 1 1 2 3 and 3. This is the transpose.
Mm.
Oh. Mm, yeah. Yeah. Okay. So yeah, you got this, and this is your P now, and this is Q, which is anyway semi standard Young tableau. Right now P is this P again uh, is now semi standard Young tableau. So this is your answer. So um, yeah, dual of RSK A is equal to, now I'll just write what exactly we got: 1 1 2 3 3. And this is 1 1 2 2 2. Yeah, so this is DRSK, and this you got exactly this RSK is that clear? As you can see, these are different, these are not same.
Yes, ma'am. Yes, ma'am.
Okay, so okay, then let's try with the bigger matrices, so we'll get better idea. Okay, so A is now this matrix. I'll write it again: 1 0 1 0 1 1 1 1 1. Let's add an extra page. Yeah. So now again what we will do, we'll write the by word or by vector. So you'll get
1 1
yeah.
1 3
Hmm.
2 2 2 3
Hmm.
3 1 3 2 3 3.
Yeah, exactly. Very good. So we have
And
this.
P is insertion.
Yeah, now insertion.
Q is recording.
So P I'll not write because what we are getting the transposer. So we can write just P
Mm,
dash, better we'll write P dash. And
mm.
this is recording tableau. So this is your Q. Okay, so we again start. So you have 5, you have nothing firstly. Now you insert 1.
Insert 1
Hmm.
and 1.
Yeah, so
And the recording section is 1.
yeah, so you get 1 1. Now next step you insert 3.
3
So what will you get? You will get 1.
1 3 1 3 1 1. This side Q side is 1 1.
Yeah,
P side is 1 3.
exactly. Very good. Now we'll insert next
And
one
now
is
2
2.
2.
Hmm.
So 2 is 3 is greater than 2. So we pumped out 3 is next row and we insert 2.
Yeah, exactly. So we'll bump out and then in the second row it will just be 3.
3.
And yeah, corresponding to that we have added the extra box in the second row which will record the
Second row.
position as 2. Yeah.
Mm.
And now we'll insert 3. Next one is 3. So you'll get 1. So in the first
There
row,
1 2 3.
yeah, exactly. There is nothing to do much here. So you'll get 1 1. So extra
1
box
2.
is 2.
First row comes 2.
Yeah, exactly. Now the
Next
next
is
number
1.
is, yeah, now is the difference.
New one. We insert new one. 2 3 and 1. 3 will go next line, ma'am.
Yeah. So firstly, so you are inserting 1. So
Next
how?
one. New one will come.
Yeah,
And
exactly.
2 3. Next is 1 is bigger than 3. So 1. And the next row is 3.
Exactly. Yeah, this is right. And we got the extra box at this
1
place.
1
One,
2
one, two, two,
2
and
3.
corresponding to 1, it
Third row
is
is
3.
3.
Yeah, exactly.
And insert 2.
Now this is, yeah, we need to insert 2. So what will,
1. New 2 we insert first row.
exactly.
3 1 2 and 3.
1, 2, and here 3. Exactly.
3.
Yeah. So what we
1
did,
1 2
yeah, then, yeah.
2 is to 3.
And the position is
Second row is 3.
3. Yeah. So what we did, the same number has been bumped out, and when we inserted 2, so this is exactly 1. So we will just write to the next the number 2, and yeah.
Next we insert 3.
Yeah, we have to insert 3 now.
1 2 new 3. And the second row is everything is less than 3 only. So 1 2 3
Yeah,
3.
exactly.
1 1. This side 1 1 2 2 3 3 3.
Yeah, exactly. So the only difference where the difference came, because the equality we are also looking. So otherwise in RSK, the new number, the number 3 would have come in the first row itself. 1 2 3 3. That is the major difference.
RSK we didn't see equality, just
Yeah, the
bigger number only.
exactly. So this is the
And the
final.
transpose
Yeah, so this is your
and the
P
transport
dash.
of P.
Yeah, exactly. So this is P dash and this is Q. So P will be 1
P
1
will be
3
1 first 1 1 3
2 2
2 2
and 3
3
3.
3.
Exactly. So this
And the Q
is
is same.
Q is same. So we got Q to be 1 1 2 2 3 3 and 3. Exactly. So we got this. Right. So this is your dual of RSK of A is P comma Q. Right?
Yes, ma'am.
Okay. So very good. So this is okay. Okay. Let's move to the next question then. Now what you need to do, you need to find A when you have given that what is the dual of RSK. Let's see. So now you have P and Q. Actually, yeah, P and Q. So DRSK A is given to be 1 1 1 2 2 2 3, and the other side 1 1 2 2 2 3 3. Right. Now, as you can
Yes,
see,
ma'am.
this is Q, this is P. But what when we do, so what we need to do, we need to just uh, trace the
First thing,
yeah
P.
yeah. So we need to just trace the steps what we did to. We just need to write the. We just need to retrace the process which we did for uh, to find DRSK. So now let's see what is happening. So first step is we do the transpose. So so whatever P is, we will consider P dash. Then only we can do a thing. So the transpose will be what? 1 2 3
1
1
2
2
3 1 2
1
1
2.
2.
So we got this. And the Q, you know. So yeah, I'll
Mm.
write Q once because we need to just look at P and Q and find out what we need. Yeah. So this is P and this is Q. Sorry, P dash. Because we did the transpose to find the P, so we need to get back the matrix. We need to do the transpose again, and now we will see how we are going to get. Uh, Again, what we will do, what we have inserted, we need to remove. That is the process. So now you have P dash and Q. Now what Q is telling? Q is also, we need to find the bivector. Sorry. Yeah. We need to find the bivector. As you can see, the entries are 1 2 3 4 5 6 7. So there are 7 ones in the because you know that we are the matrix A is of 0 1 only, because dual of RSK we are only calculating for the matrices which are of 0 1, and it has even be asked like A is a 0 1 matrix. So as you can see, these entries are 7. So 7 non-zero numbers are there in the matrix A. Okay. Okay. Let's
Yes,
see.
ma'am.
So the biggest number is 3. So last time, as I said, we are not looking at the full 0 column or 0 row in the end. We are not saying if it comes in the middle, then it's okay, because the corresponding position will be like, if fourth row has something which is non-zero, then we have to consider 4 in the tableau, right? So so this is kind of 3 cross 3 matrix. So we'll just we need to find the 3 cross 3 matrix corresponding to P dash and Q. So now what we will do, we will bump out sorry, we will remove the numbers and write the bivector corresponding to that. So as you can see in this Q, the last, so firstly this is what this is recording, this is recording the row number,
Row numbers.
right? So row number says like the matrix whichever you are getting, so the row number should be, so in the end, so you always write bivector in the increasing order of sorry, weekly increasing order of row vector.
Weekly increasing.
Yeah.
Mm.
So so the last one must be 3, because 3 is the last the matrix is 3 cross 3. So the last integer must be 3, like sorry, last row number must be 3. and Q records only the new box. So new box must be in the end like 2, 2 or 3. So as you can see, this is the only option which can be inserted. So 3 is the row number, and corresponding to that, this number has been added. So 2 has been added, right? So 2 has been
Yes, ma'am.
inserted. uh, Sorry, what I'm saying, I'm saying this is the new box. So new box means when we inserted it, the extra box must have been inserted at this place. So what we need to do, we need to remove 2 now. So okay, I'll copy this. Just think of what we do to find P and Q, and just retrace what we did to find it out. So 2 must be, now 2 must have to be removed. So okay, we'll remove 2. So 2 has been inserted here and it went to this box. So now we'll make it to move at the second row. Now second row means you must have inserted 2 like, so what I want to say, this is 2 is your AI. Okay, so now we need to remove the remove what we have we must have tried to insert. So as you can see, we look for A such that A is less than or equal to I. Now AI is your 2. Okay, now we need to look at A such that this would have happened. So as you can see, equality is there. We must have removed, we must have bumped 2 out and inserted 2 at that place, because equality is there, because we can insert the same number, because we allow A to be equal to AI also. So here what we need to do, so 2, this 2 must have been removed, will be removed, and this 2 AI must be inserted. So what we have done, that 2 must have been inserted. So I'm writing the so inserted means this we have done that. So as you now, if you want to check that, if you insert 2, this 2 will be removed and it will move to the next box. Is that okay?
Yes, ma'am.
So arrow we always write what we did, what we really do in the insertion case. Okay. Now this number, now we will move to the first row. We need to find out this number which we must have inserted. Now
Again, 2.
2 must have been bumped out. So this 2, as we can see that 2 is equal, equality is allowed. So this 2 will go out and this 2 will be in. So what we must have done, we must have inserted 2. So this yeah, so this is 2. Is that okay? Yeah, anyway, we don't have anything. So 3 and 2, you got 3, and corresponding to that you got 2. Okay, let's
Yes, ma'am.
move, yeah, let's move to the next one. So next is now the insertion tableau you have, sorry, recording tableau you have 112, 112, and 223. So 223, you have this now. Next step is this. Okay, and next step means now 2 we can remove. So this is your P dash, new P dash, or maybe we can number it, but we don't know how much. But yeah, these are 7 numbers, so we must have started with 0 and let's say 7. So let's say this is the 7th step. So this is 7th step, this is now 6th step. So this is P dash, this is Q. Okay, let's see. Now again we will look for the biggest number in terms of row. So Q is recording the row number. So the biggest number we have is 3, which could be the extra box, the new box. So 3 must be there. So corresponding to that we will see this. So in this pi vector we have 3, and corresponding to that we need to figure out what is the number.
One we pumped out and we insert one. Again one comes. Again one will come. So one, two,
Exactly.
three, 1, 2.
Yeah,
It's a P
exactly.
dash.
1.
So
Yeah.
one is the
Right, exactly. So if you bump out 1, then this will go, and 1 must have been inserted here because 1 is the same number. So this is the new one. These has been replaced, and then again when you put 1, like these have been replaced because equality is allowed.
yes.
Exactly. So in the sixth step, so in the fifth step you got
1, 1, 2, 2.
1 2 3 1 2, and here you got 1 1 2 2 2. Exactly. Okay, now let's see the next number. What must be the next number? Next number is 2, because in Q you are looking for the you are looking the next row you must have inserted, like next row number you must have inserted. So you are going from the right, so this must be
2.
2. And now let's see which 2 you are looking at. So as we have seen,
Down.
yeah, so as we have seen, we consider the rightmost one. So that was the theorem. So we are always looking for the rightmost one. So rightmost one is this. So we must have we need to remove this too. So now let's see. So this number. So this number, as you can see, this must be the number, right? Because it
Yes,
cannot
ma'am.
be something else. So this is 3.
Ma'am,
Because
this step again one more step.
yeah, yeah.
Because what I did means before we take last number is 3 and we insert the same way I did.
Yeah.
Here myself I did. And
Okay.
madam took first row.
Yeah, yeah. I took this first row one. So what I did,
Uh,
so what we
mm,
need to do here, so this is your insertion, this is the recording tableau. Now
mm,
there are two options
mm,
to consider too, right? So
mm, mm, mm,
either, because extra box is always in the out one, like either in first row, second
mm,
row, the last one it will be. So there are two options, either this or this, both can be the option,
mm,
right? Now from the
mm,
theorem which we did, which have been discussed, if you for the RSK thing, that you can check, this will work for dual also. So yeah, here this is the theorem. So this is the lemma.
mm.
So this lemma
Okay,
says
okay.
we consider the rightmost. So when we have the case like the numbers are same, then we will consider the
Mm,
rightmost one. That must be the next one. So um, okay, but definitely we need to prove it for this, because this is for the condition that P is in SSYT. But the point is, this is anyway. So P we are considering of from the right one. Okay, right one means what I should say. Okay, no. So basically, this lemma is for semi-standard Young tableau, but we need to prove it for this for the new one, because this is not semi-standard, right? The transpose is
mm,
semi-standard. But if you want to verify, so the best part is we are only considering 0 1 matrices, right? A is
mm,
0 1
mm,
matrix. So now what will happen? So as you have considered 2, okay, so if
mm,
as you can see, there are two choices, either this or this. Even there are three choices, there are three twos coming in this picture.
mm.
And
Yes,
you
ma'am.
know that one is going to be at every like one, either A could be, so the matrix is 3 cross 3 matrix, and the entries are either 0 or 1. That means if 2 is repeating 3 times, that means, and you know that either it is 0 or 1, so the by the entry it must have repeated only once, because entry is 1
Yes,
or
ma'am.
0, and still you are getting 2 2 2. That means there are 3 columns. There are three
Yes, yes.
columns, so that means 3 columns means first column, second column, third column. Oh, sorry,
Mm.
the row number, sorry, not the column. So this Q considers row number, right? So row number,
Yes,
we
ma'am.
are saying there are three rows with non-zero
Two, two,
entry.
two.
Yeah, 3 rows. So
Mm,
that means
mm,
it
mm.
must be so second row. Sorry, you must be having 1 1 1 here.
One, one.
Yeah, but
Second row, third, second row, first, second row,
yeah.
second.
So what you can do, there is one way to see this. So in this place at least, you can check whether the, because I yes, exactly, we cannot use the lemma, but the point is you have 2 2 2 here. So the question is which two you must consider, right? So you have one one
Yes, ma'am.
two two two. Which two you must be considering? So either this or this. Now the corresponding number you can check. So if you consider this two, so if you consider this two, you must be getting 3, right? And we always
Yes,
write
ma'am.
from left to right. Okay, so you
Yes, ma'am.
must be getting 3 at this place. Okay, and that
Yes,
is
ma'am.
possible,
Mm.
that is possible when you are considering in this way. And as I said, 2 is repeating 3 times, so second row must be 1 1 1.
Yes,
So
ma'am.
one more thing, so to verify this, for example, if this would have been bumped out, sorry, this
Yes, ma'am.
would be the new position, let's see. If this is the new
Mm.
position, then 2 must be here. Now this 2, uh,
Yes,
okay,
ma'am.
yeah, this 2 means you have, so you must be inserting this 2 in this row, and then when it moved to
Mm.
the previous one,
First step.
this
Mm.
2 must have been replaced, but
Yes,
you would
ma'am.
have got 2 only. So 2 must be
Yes, ma'am.
inserted, and that is not possible. uh, Okay, that is not possible in this case, because you know that at the position 3, 1 is there, because
Mm.
there are 3
Mm.
twos
Yes, ma'am.
here. So by that you can definitely say that this 2 must be from this side.
Yes, ma'am.
Yeah, but the lemma, maybe there would have been a lemma, but I'm not sure. But at least you can check, you can try both the cases, and you can observe that which one is going to be correct, because that you can do. So what can you get in both the situations, that is the major point.
Okay. Mm. Okay.
And the main thing is A is with just 0 and 1s, so there is no
Mm.
repeating of the
Yes, ma'am.
row number and column number, exact row and the same row and column number, right? So this must be the 2. Yeah, oh, okay, I'm anyway writing the steps, right? So sorry, this is the 2. So you must have removed this, and you got here. So sixth step is 1122, and here you again got 1122.
One, one, two, two. Mm.
Now the next
Next,
number
we picked
is,
out
yeah, this
two.
one.
Two means again two.
Hmm.
Two, two.
So
Again
this,
two, one means one, two.
the new one. So this must have been
Mm.
replaced, right?
Mm.
So 2 you will
Yes, ma'am.
remove from here, and if it go to the first row, then this must be switched, because equality is allowed. So you
Yes, ma'am.
must have been getting 2 2, right? 1 1 2, and here same 1 1 2. Now the next one is this 2, and this 2 means this 1. So you must have
One.
inserted 1. So 1,
Again one will come.
yeah, so this will go, and this will be inserted 1, and then this must have been replaced because equality is allowed. So you got 1 2 1. So 2 1.
Again 1 2 1 1 ma'am.
Yeah. So you have 1 2. This is 1 1. Now the,
1 we take
yeah,
means
this
2
one, and this one.
2.
Exactly. So 1 2. So this is 1. This is, oh sorry, row number na. So 1 2. The row number is 1 and the column number must be 2. And the ninth is 1 and 1. You must have got 1 1. And then it's just empty. Oh, I started writing in increasing order. So this is 6 5 4. We are tracing back now. So this is 4 3 2 1, and zeroth step if you want to write is just nothing. So
In RSK also we used the same procedure, ma'am.
yeah, same procedure. So if we, so there's a bijection. So the point is there's a
Mm-mm-mm.
bijection. So we must be, so we should know what exactly the inverse. So inverse means we should be able to write the matrix corresponding to those P and Q. That's the major question.
Yes, ma'am.
So
Mm-mm.
that's why we are doing this. And from this you can see this bivector you got. Now we need to retrieve the matrix. Oh, paste. Yeah. So the matrix will be what? 3 cross 3 matrix.
1
Hmm.
1 1 0
Hmm.
1 1 1
Exactly.
1 1 0.
Hmm. Right. This is 110. Yeah. So yeah, I hope. Yeah, if there is a lemma, I will tell you next time. But
Okay,
if
ma'am.
not, anyway, you can always try because that lemma is itself you can check in the example itself, because if there is a lemma then it must be applied to that example,
Yes,
and
ma'am.
even in the
Mm-mm.
example you can do the same thing. So it's nothing
Mm.
you always need to remember these things, but you can always get to know from the question itself. Okay, so yeah, this is the matrix A which you will be requiring. Okay, very good. So let's move to the next question. Yeah, this we discussed. Okay, so I hope this RSK and dual of RSK is clear.
Yes, ma'am.
Okay. Okay, let's do this question then. Now we will do basis thing, how to get symmetric functions from different bases, and if you have one basis, can you convert it to the another basis, or these kind of questions. Let's see.
Yes, ma'am.
Yeah, I wrote the formulas because there are some formulas, but you can uh, try. Oh, yeah, it's easy, but I just wrote it for the reference. Okay, so write E3 comma 1 and H3 to 1, 3 to 1, 3 to 1 in terms of monomial symmetric functions. Yeah, polynomials. Yeah, better to write polynomials. It's fine anyway. Yeah.
Ma'am, can you ask this type of in theorem? They will ask theorems that this equation solving section means
Mm-hmm.
we have to write theory part, and we are just proving this self. If E lambda mu means m lambda equal to some kv, what is a kv, or we have to write that type, and we have to theoretically we have to explain.
I don't know exactly how will be the paper because yeah, I cannot comment on this because I don't know exactly. So
Okay, ma'am.
yeah, better to try to understand the process, because anyway if you want to remember these for the long term, it's better to
Yes, ma'am.
remember the proofs, because that will give you
Okay,
the
ma'am.
idea, intuition behind all these things. Yeah.
Yes, ma'am.
Yeah, I have no idea like how exactly will be the paper, but yeah, you can try to understand this, and I think
Mm.
if that is the case, then you will always be able to write the proof. But yeah, I
Yes,
don't
ma'am.
know exactly what will happen. Yeah. Okay. So write E3 3 to 1 and H3 to 1 in terms of the monomial symmetric polynomials. So let's see. We did that anyway earlier. So how, what is this? This is always, so lambda is from partitions of D. The other way to write is lambda is from the, this is a way to write it. So we can use that. This is a way to write mu belongs to partition of T, and again there is no limit on n, so we are assuming that n is big enough. N means the number of variables. Okay, so this is n lambda mu m mu x. Okay, and again h lambda considers the corresponding m. So what are these n and m? So uh, okay, I'll write h first, that will be better. Yeah, anyway, okay, it's fine. And h lambda x is equal to summation mu addition of t. So this is m lambda mu m mu x. Okay, so yeah, now where n lambda mu, what was n lambda mu? Number of semi standard young tableau such that, sorry, this is not the way. The number of,
Matrix.
yeah, number of matrices, yeah, exactly. So yeah, number of matrices with
Row column is lambda.
hmm,
Column sum is mu.
yeah, row
Row
columns,
sum uh,
and column sum is, oh yeah, column, what I wrote, row sum is lambda,
column sum.
hmm,
Mm.
is mu, right? So what we are looking for, we are looking for the matrices. Yeah, so for example, if lambda is equal to, yeah, okay, we'll write it in the, so this is not yeah, and the entries are from where, number of z plus,
In n is
yeah,
0, 0, 1.
yeah, for n this is 0 1, so I'll write this to be n, and the n
0, 1
hmm,
matrix.
exactly. So n lambda mu is number of 0 1 matrices with row sum is lambda, and column sum is mu, exactly. Yeah, so let's try to do that. So this is one way, and there is another way. Another way means you consider this, so that's why I kept the formula. So this has been proved that m lambda mu is equal to the sum over all those partitions nu, such that k nu lambda uh, such that m lambda mu is equal to the sum, oh sorry, yeah, m lambda mu is equal to the sum over all those nu in the partition of T with uh, with the values k nu lambda k nu mu, right? So what I was saying, m lambda mu is equal to the sum over all those nu, be whatever you want to write, PD, such that this is k lambda nu. The order matters, as I said. The first one is shape, and the second one is type. So it
Type.
matters, yeah, so it really matters what you are looking at. So, and this is, let me check if I wrote it correctly. No, so this is in the first place. Oh, better to write v, that's fine. It's just new only. Sorry. So this is lambda nu k mu mu. Okay.
No, ma'am. Mu lambda k mu v. V lambda.
You are saying other side? No.
You see.
Okay, okay. Yeah.
Mm.
First one is new. Yeah, thank you.
Mm.
So this is new and lambda nu mu. Okay. Product doesn't matter. So it could be m mu lambda or m lambda mu, doesn't matter.
Mm.
Okay. Yeah. So let's try to find it.
Ma'am, now also again same you write. Correct, ma'am. Correct, ma'am.
Correct, na?
Correct. Yes.
And yeah, and for yeah, so let's try to find this m lambda mu. So what does this say? You will be finding k nu lambda and k nu mu, and these are the partitions of D only. So let's consider our question. So our question asks for E321 and H321. So this is for H. So H321 we try to find. Okay, let's see. So for H321, yeah, the partition is so we are partitioning 6. So D is equal to 6. As you can see, 3 plus 2 plus 1 is 6. So we are partitioning the number 6. And yeah, and what is K nu lambda? K nu lambda is number of semi-standard Young tableau such that type is new and shape is lambda. Sorry, that way around. So this is type.
Shape.
Oh, again. Yeah, it's
Shape.
Yeah, exactly. So this is shape. This is type. So let's see what can we get. Right. Now, firstly, we are writing the sum over this. So these are the sum we are looking at. So first we will consider mu, and corresponding to that lambda we already know. We will consider mu, and we try to find the value. So I'll copy this. Yeah. So what we will try to find now, we need to, so first consider what we are looking at. So firstly, mu is the partition. So mu, what are the partitions of 6? So you have 6, 5 plus 1, 4 plus 2. As I said, keep it in a order so that you will never forget any number. Now 4 plus
1, 1 plus 1.
Exactly. Next.
3 plus 3. 3 plus 2 plus 1.
Exactly. Very good.
3 plus 1 plus 1.
And 2 plus
2 plus 2 plus 2. 2 plus 2 plus 1 plus 1.
Exactly.
2 plus 1 plus 1 plus 1 plus 1.
And next is
and 1
4.
plus 1 plus 1 6 times.
6 times, exactly. Very good. So we have all the partitions with us. Now first we'll start. Okay, I took a bigger question, but that's okay. So we need to find for 6 first. So mu is 6. So how many n lambda mu we are going to get? That's the major question. So number of semi-standard Young. So for n lambda, and now mu is what? Mu is okay.
Number of partitions.
Yeah. Number of So mu is now 6. First we have considered with 6. So if mu is 6, what will we get? And lambda we already know, right?
0.
Lambda, yeah. Okay.
0.
Is it? So 1 second. What we are looking at? E321. So this is not. Okay. Again I wrote. I'm looking for m.
Lambda.
Yeah.
Lambda equal to 6. V equal to.
Lambda is equal to 3 to 1. That is the partition.
3 to 1.
Yeah. And now we
Mu
need to,
is 6.
yeah, m, so we are looking at 3 2 1 and 6. This we
N,
need to find out.
um,
Now from the formula, what does this say? This is equal to the sum over k mu new acha, okay, it's just the product. First one will be that. So this is 3 2 1 and k new 6, right? And new is a
this one.
partition of d is 6.
Mm,
So now what you need to do, you need to find the Koska number. So Koska number
mm,
corresponding to this. So you are not given the shape, but the type is given.
mm,
So type is given means
this one.
3 ones, 2 ones, sorry, 2 twos, and uh, 1
1 threes.
threes. Now,
Threes.
yeah, exactly. So how, okay, so what new you can consider so that you can have that. And the other thing is, okay, so we need to figure out both the things, like this number and this number. One more thing, both of them should be non-zero to have at least one value, right? Both of them has to
Mm,
be non-zero. So you are looking at some shape new such that this happens, this will satisfy, and shape, and this is a partition, so this must be from all these options, right? Shape new. So this looks complicated, but it's not really, because if you if you know how to deal with that, you can easily calculate these values. So 3 to 1, and the other thing says 6 ones, so you have just ones to all the
this
position
one.
6. Now can you tell
1.
me, so this is on, there is only one option for this.
That this is not a semi-standard
Hmm.
tableau.
So you, no, there is one option for omega.
Okay, okay. One row
Yeah.
we can give.
Because all ones can be there, because this is semi-standard young tableau. So there must be,
Mm,
there is one option of keeping weekly increasing, but over the column you need to go in the increasing order. So this is the only option. But does this mu satisfy this value? So you are looking at this. So you have 6 places. Now 3 ones, 2 twos, 1 threes. So there is one option, as you can see, only one option,
mm,
right?
yes, ma'am.
Is that okay? So now, so there
The
is one
both
option.
condition comes
Hmm.
same semi-standard tableau type.
Yeah. If
Shape.
yeah.
Type we have,
Mm-hmm.
and we try to find tabula. So both condition it gives same
Shape.
tabula.
Yeah,
First
exactly.
row means
Hmm. So
used
can
first
you
row.
find a shape such that both of these type can be fitted in that shape? That is the major question.
Okay,
So
okay.
what we tried, we started with one and we come up with something, because that is the only option. And we went to this
Mm,
first part, and that we can see that there is only one option to keep those things in one row, right?
okay.
Because
Mm,
there is no other option.
mm,
We need to keep it weekly increasing. So all the numbers is to be in this order. So
yes,
so
ma'am.
we have 1 into 1. So with this case you got 1, right?
Okay, ma'am. Mm,
And if you want to see the in the matrix thing, so in the matrix thing, what must have been happened? So we want row sum to be 3 to 1. So this should be 3, this should be this, and the column sum should be 6, right?
mm.
And there is just one.
Only one column.
One column.
Mm,
So as you can
one
see,
column.
what we can do, we can just keep 3 to 1.
3 to 1.
Right? So there is one
Yes,
option,
ma'am.
and that is the only option. So both of these is fine as long as we can handle. Okay, so yeah,
Yes, ma'am.
now let's try with one more, and then I guess you will get the idea. So we can skip. So let's try with 5 plus 1. Okay, so this is 5 plus 1 means 5 comma 1, it's the same thing. So this is now your mu, and lambda is again same. Lambda is 3, 2, 1. If the coefficient of one of them has been asked, you can just try to calculate with the same. So mu is exactly what? Mu is giving you what is the coefficient of m51 in the summation. So if you have been directly asked what is the coefficient of m51 or what is the coefficient of m11111, you can just directly calculate for this question, for this part, and you can answer that. You don't need to write the full polynomial, sorry, full function.
Tabula.
Yeah, table, like for all the option, all the partitions, you don't need to try to calculate. Okay, so this is the case. So let's calculate with this again. What we need to consider, we need to find out m lambda mu, which is equal to k lambda,
Summation.
yeah, nu.
V lambda mu
Yeah, exactly. So what we are saying, mu is 5.
m.
This is 3 to 1.
Lambda
And
is 3 to 1, mu is 5 comma 1 is equal to summation beta tends to d
d is
k
6. K
gamma
yeah,
gamma 3
k
comma 2 comma
nu.
1 k gamma
Yeah, this
5
is
comma
new.
1.
Yeah, new 5 comma 1, exactly.
And
So
first one is 3 ones, 2 twos, 1 threes, and the second one is 5 ones and 1
yeah,
twos. And
right.
first row is 5 column we assign 1 and the second row we assign 2 only. Using this we write the
Yeah, we need to write according to these conditions. So we need to find the type
mm,
new
mm,
such that this happens.
mm,
So let's see. So again, with this, so always look for what is better. Like as you can see, 5
mm,
ones are there. So you
ah,
always know ones should be in the first row, because if it go to
mm.
the next column, sorry, next row, then the earlier one must be cannot be. So this condition will cannot be strictly
Cannot
increasing.
satisfied.
Yeah.
If we choose first one, we can't assign 1 1 1 everywhere.
Yeah,
The
exactly.
tabular condition will be wrong.
Hmm.
So
So
we used the second one. First row is 1 and the second row is 2.
yeah, that is one option, but there are two
So
options again, because you either
mm,
can have this
you put 2.
uh,
Yes.
1 1 1 1. So you have 1 1 1 1 1, and you can have two here. So that is one option.
Uh,
There are two options to do this. Now let's see which one is satisfying the earlier case. So type new.
mm,
Now 3 ones are there, 2 twos are there, 1 threes are there. So as you again
mm.
can see, we can put it in the same row, the same thing
Same
which we
row.
did. 1 1 1, 2 2, and 3. And for the other part, when you have this, also you
1
need to
1 1
find
2 2 3.
1 1
1 1 1
hmm,
2 2 3.
2 2 3. But as you, can you get something else from in this type also? Can you put it in
Yes, ma'am.
another way, like, so you have 1 1 1, that has to be in the first row.
1
Now what you
mm,
can have, 2 here, and
mm.
2 can be here, and 3 can be
2
here.
can be.
Yeah,
Mm.
because it's still this satisfies weakly increasing and strictly increasing condition. So you have two
Yes.
options for this. So k nu lambda is equal to 2. Lambda is your 3 to 1.
Mm.
So this is 2, and with this that sorry, okay,
3 comma 2 comma 1
yeah,
is 3, ma'am.
3, yeah, this is 3, and this is 2.
K
Hmm.
5 comma 1 is 2.
Hmm. Oh, one second, one second.
6.
So how will you write? Don't write like this. So in both
Mm.
cases type has been different. So this type is a different type, this type is a different type. So with this type,
Mm.
so when you consider new to be just 6, this is your type, right? So corresponding to
Yes,
this,
ma'am.
k6 3 2 1 is equal to 1, k6
Mm.
5 1 is equal to 1, because when you have considered this type, then both of these giving the value 1, right? And when nu is equal to 5 1, then what you are getting 5 1 3 2 1, you are getting two options, and from the other part you are getting 5 1 5 1, so you are getting 1, right? There is just one option here.
Yes, ma'am.
So from this, so in m lambda, yeah, I'll write 3 to 1, m3 to 1 comma 5 1, you are getting uh, you're getting so 1 with
3.
this, so you are getting 1 into 1 plus 2 into 1, so this is 1 plus 2, that is 3, so you're getting 3 from here. So likewise you need to calculate for all the stuff, but yeah, this is 6 is a big number, so there are many partitions, like number of partitions are big, so you need to consider for everything, so that is the question. But if you have been asked for which m new, you can find out the value, like if you have just been asked calculate, for example, 2 comma 2 comma 2, the coefficient of, so that you can directly calculate using this part, or you can do matrix thing, you can do Koska number thing, both are fine, right? Whichever you find it interesting. Is that clear?
Ma'am, then k of 5 comma 1, 3 comma 2 comma 1. Then gamma of 3 comma 2 comma 1, we get 3.
uh,
3 types now.
Sorry, come again.
K gamma of 3 comma 2 comma 1.
K gamma k nu of 3 comma 2 comma 1, you're
3
saying?
comma 2 comma 1, we get 3.
Yeah, we got 3.
K,
Yeah.
K.
K, no, we have not got 3.
K,
No,
3 types we can assign now.
this one you are saying?
3 types of
No.
tabular we
So
have.
the point is this type is different and these two types are different. So
Okay,
what we
ma'am.
are saying, what I did, what I wrote, the new is different. So when you have considered new to be 6, so the summation is over new, all the partitions new, such that both of the options has corresponding, like Koska number you need to find for that mu and the type 3 to 1 and the type 5 comma 1. So when you have considered nu to be 6, then you got Koska number of 6 3 to 1 to be 1, and Koska number with shape 6 and type 5 comma 1, you got 1. When you have, so this is the case of this one, this case, this case and this case.
Okay.
As you can see, you got 1 and 1, and when you switch to nu to be equal to 5 comma 1, we got two options with 3 to 1 and one option with the
5. 5 comma 1.
I wrote type. This must be shape. Sorry. Yeah, this is shape, you know. So we are looking.
Type
No.
3
Type
types
is
of
this.
1, 2
Type is
types of
this.
2s.
So this is type. I wrote for new. This new is the shape. New is the shape and type is telling you how many 1s, 2s, 3s you are considering. Right, so with shape new 5 so when you considered 5 comma 1, you got new is equal to 5 comma 1, you got Koska number with the shape 5 1 and type 3 to 1, you got 2, and Koska number with shape 5 1 and type 5 1, you got 1. So this is the case. So corresponding to that, m is what? That's why I wrote it in this sense. So you have summation new partition such that k new 3 to 1 and multiply it. Inside only 5 comma 1, and in this you got only two options for the shape. So shape either could be 6, You can write for every option, but you will get 0 because there are only two choices to keep it, right?
Mm.
This
Yes,
plus
ma'am.
k 5 1 3 2 1 into k 6 3 2 1. Sorry, uh, oh, what I wrote, not this. This is 5 1 and this is 5 1 comma 5 1. So with this you got k6 3 2 1 is exactly 1. This is 1 plus this is 2. This is 1. So you got 1 plus 2, that is 3. That's why I wrote in this form. So you will consider all the options. Is that clear now?
Okay, ma'am. Yes, ma'am.
So this is the process to find homogeneous, complete symmetric polynomials.
Symmetric polynomial in terms of monomial
Yeah,
symmetric.
exactly. Now you can also do for elementary symmetric polynomials. For that, what we need to do, we need to consider, uh, so according to the, so either we can just consider 0 ones matrices, and that's why RSK is related to this. So we got these
Mm.
formulas using RSK only. Like the
Mm.
one is by RSK, the other one is by dual of RSK. So here you
Mm.
can see you got new dash lambda, and this is, so new dash,
New
yeah, new u. So what is new dash? Uh, sorry,
transpose
transpose of what?
V. New
No, no, no. It doesn't matter, no.
transpose of V. Mm.
No, no. How will you do that? So, for example, new is a partition. So this is, for example, 3 to 1. Then what is the transpose? It doesn't transpose in
One,
what
two,
sense?
three.
No, no, no. It's not like that. That is for the
Mm.
tableau. So
Mm,
so
mm,
think
mm.
about in the terms of tableau. What is happening? You have some tableau. Okay. When you do the transpose, what is happening? This is becoming, the rows are becoming columns and columns are becoming rows, right? So
One, two, three.
so three ones, no, I
Two
need to
twos,
see.
one ones, one threes.
Mm, three ones, two. So for example, if you got like this is 1 1 1, this is 2 2, and this is 3. When you transpose it, then you will get, but that is not the case. Like, that's what I am saying. This is related to Cosca, so I forgot. So I can actually check. um, I think that you can, it was defined earlier itself. It is a lambda dash. Mm, it's not the inverse. Yeah, these are dash, no? So
Mm.
dash is actually what it is doing. Mm, yeah, lambda dash. E lambda dash, right? So it must be here. Yeah. So if lambda is, yeah, see, if lambda is 532, yeah, then when you will so when you will do this, so for example, if lambda is 532, oh sorry, this is 532. So 5 boxes in first one, 3 boxes in next one, and 2 boxes here. So you have this, right? So when you will transpose it, you will get three boxes. So first column will become three.
Three boxes,
Yeah,
three
three
boxes, two
boxes.
boxes, one boxes, one boxes.
Yeah, two box, one box, one box. Yeah, exactly this which has been written, this one, right?
Mm.
So according to this, what will you get? So lambda dash will be conjugate is 3 3. So you'll just count the 3 3 2
Mm-mm.
1 1.
2, 1, 1.
Yeah. So for example, in our question, so if you want to find out the, so for example, if you want to find out for 5 1, for example, this is 5 1, what will you get? Sorry, you will get 2
2, 1, 1,
1
1, 1,
1
1.
1 1, exactly. So you'll get 2 1 1 1 1. Okay. So
Yes,
using
ma'am.
this, so whatever you are considering, use this and find this. Find the value of yeah, this one. Okay, exact same thing. Just you need to consider new dash. Okay.
Yes, ma'am. Low battery.
Yeah, I'll connect the charger if needed. It's
Mm-mm.
10%, so hopefully it can continue for half an hour. Okay. Yeah. So is that clear? Can you calculate it?
Yeah.
Or should I do?
Yes, ma'am.
Okay. Great. Yeah, I took some big example, I think. 6. Okay. So let's move to the next question. Write H221 in terms of elementary symmetric functions. So you have given H21. You need to calculate it in terms of ease. Elementary e mu or e lambda, whatever you want to write. So you need to find out this. Okay, let's see. So again, I wrote some. So this is exactly using the generating function. So using that, we can actually calculate these polynomials in terms of the other bases. So yeah, so e minus t h t is equal to 1. So this is something, the relation, this is the relation we are having, and using this, so e minus t is what, from the elementary functions you'll get so you'll get minus 1 raised to power n, and this is your ht from the complete part. Now now as you can see, this is equal to 1, because if you have seen the proof, this is e minus t is something 1 by 1 plus t xi raised to power something, and and ht has this upper part. When you will multiply, it got cancelled and you'll get just 1. So this generating function is being evaluated to 1. So now what will happen? Uh, this means for all n greater than or equal to 1, this must be 0, right? Because this is 1. So when you take just the coefficient, when you take n is equal to 0, then what will you get in the first part? You will get when n is equal to 0, you'll get t raised to power 0 minus 1 raised to power 0 e 0, and here you will get h 0. That is equal to, because both are 1, so you'll get 1, right? Now
Yes,
because
ma'am.
you can just consider the constant, so there is just one monomial
Yeah.
with this, right? And now for the other, so 1 is already there, and now you will and for the other parts you will get some power of t. So you must be getting, in this generating series, you must be getting zeros afterwards, right? So zeros
Mm.
afterwards means this equation must be satisfied. So what exactly is this? You are comparing the powers of t. So the powers of t, you consider some power, for example t only, t raised to power 1, and from the other part, now you will, so t raised to power 1 to, in this multiplication, when can you get? When you consider some, so you will consider t raised to power 1 here, and at some time you will consider t raised to power 0, and you multiply, you will get the power of t to be 1, and other way around you will consider 0 here and you will consider 1 here. So you need to consider all the options, which you can do to multiply this. And yeah, so you got this, right? So, basically you are summing it up. Okay, there are two sums, you are multiplying and you are comparing the powers of t. So from this, what we got, summation r is equal to 0 to n minus 1 raised to power r e r h n minus r is equal to 0 for all n greater than or equal to. We are going to use this thing to have our example. Oh, sorry, have our answer. Okay, so what we need to find out, h221. So h221 means h2
H2,
into
H2, H1.
h1. So you need to multiply. Okay, so 1 second. Yeah, it's fine. Okay, so this you need to find out. So for example, you need to find h2 square into h1. So let's try to find it out. We already have this much thing. So h1 is minus e1 is equal to 0. h2 minus h1 e1 plus e2. I'm just writing from these. This is coming from this equation only. You just put whatever you need. For example, just put e r equal. So for example, you just consider n equals to 1 first. When you consider n equals to 1, you'll get so r is first, r is equal to 0. In the second one, you will consider r equals to 1. So this summation you will expand. You'll get this. Now when you consider n equals to 2, you'll get this. So this is n equals to 1. This is n equals to 2. This is n equals to 3. You'll get h3 minus h2 e1 plus h1 e2 minus e3. So actually you don't need h3 right now. You just need h2 and h1, right? So what you can do, this is equal to 0. Now what you can do, h1 is equal to e1 first. Second is h2 is equal to h1 e1 minus e2, right? From this. This is from this and this is from this. Now you know that what is h1. h1 is e1. So e1 minus e2. So you can actually write it in the form of 1 minus e2, because you know that what does that mean. So this is now at the level of partitions. So this is in the form of partitions. So this is h2. So when you will write it in this equation, h21 is equal to h2 square into h1. So you will get e1, what will you get? So I'm writing first in this form and then I'll write it in this form. Okay, so e1 square minus e2, and you will do square of this into h1 is e1. Is that clear what I'm doing? Is that
I
clear?
did.
Yeah.
I complete this question.
Okay. So,
E1 power 4 plus E2 square.
E1 power
E1 power 4 minus plus E2 square minus 2 E1 square E2 into E1.
Right. So I'll just write
E1 power
5
plus E2 square E1 minus 2 E3.
Yeah, exactly.
E2.
Now what
and
you
we
can
write E 5 times of 1 plus
exactly.
E1 E 2 times of 2 comma 2 minus 2 into E 3 times of 1 and E2.
Yeah, exactly. Very good. Yeah. So you have this. So this is exactly your complete complete homogeneous polynomial in terms of elementary polynomials, elementary symmetric polynomials. Exactly. Now if they ask for what exactly is your
element in terms of complete symmetric polynomial in terms of elementary symmetric polynomial.
Exactly. So we can do that. So right. Okay. Then let's move to the next question. Write P221 in terms of monomial symmetric functions. Now you need to write it in terms of monomial symmetric polynomials P lambda. Now this is power sum. So power sum means, so P221 If we write it in the basic form, this is P2 into P2 into P1. Right? What
Mm.
is this? This is x 1 raised to power
X1
2.
square, x2 square, up to etc.
Hmm.
xn square.
Yeah, whatever we have. And I can write it a square directly, right? Because P2 is same.
Yes, ma'am.
And into you have P1, that is x1 plus x2 plus up to and so on. So this is P2 to 1. Now, yeah. So this is P2 to 1. Now what you need to write, this is now you need to find out. So one way is directly you multiply here and look at what exactly is going on. Okay, there's so this formula is exactly in that form only. So what you are doing, you are multiplying. Now multiplying means, okay, I'll write in one more way. So this is this. I'm just expanding what you have in terms of a square, and this is x1 plus x2 plus up to and so. So think about it. Now you need to find out. Okay, so why m is coming into picture? What m captures? M mu is, for example, if you are looking at m 3 to 1, what exactly is this? This is the summation.
X1.
Yeah,
Pasa.
x1 raised to power cube. So what I can,
X2 power 3, X1, X3 is 1.
this one, and x3 raised to power 1, and you
Is
will
1.
do for every exercise. Like you need to write it in this form also.
6 pattern.
Not only 6 patterns, because you don't know what count you have for exercise, right?
Okay.
Maybe it is x6 till like x6, maybe n is equal to 10, maybe n is infinity, because we have discussed that. That's why we write it in the short form, so that we don't need to write all the polynomials. So this might be, for example, 4. So all the permutations, so all the sigmas you will consider. Sigma belongs to Sn, such that this is n sigma 1, and the powers will be 3 to 1. This is exactly your m. This is the value. Now so think about it, what we are getting here. So what you are doing, uh, firstly there's a symmetry means, if you get x1 raised to power cube, x2 raised to power square, and x3 raised to power 1, you will definitely get all permutations. Like you will get x4 raised to power 3, x2 raised to power 2, and x5 raised to power 1. You will get all the possible options for these places, for these x's, distinct ones. So firstly observe that there is a symmetry already, because if you have x1 square, right, one more thing. So for example, if you have x1 square, x2 square, and x3, you will get all the permutations also. Like if you got x1 square, x2 square, and x3, you will be getting all the options in terms of these numbers, because you can always consider something else, always consider some other xi, and always consider some other xi. So distinct one are done in that sense, right? Is that okay?
Yes, ma'am. Yes, ma'am.
Now think about one more thing. So this is a partition of 5, because the degrees are 2, 2 and 1, right? The partition is of 5. But what can happen? One more thing. What can happen? You can have x1 square, x1 square, and x1 square, right? So you
Yes,
you
ma'am.
will be having xi raised to power 6 or xi raised to power 5 also, right? So what exactly
Yes,
we are
ma'am.
doing? So you have 2 to 1, but what can happen, any of them can be clubbed. So you have some figure, you have lambda 1, lambda 2, and lambda 3. So this is lambda 1, lambda 2. So 2 to 1 are exactly lambda 1, lambda 2, lambda 3. Now what can happen, this can be together and this can be separated, this can be together and this can be separated, and the other part, this can be together and lambda 1 can be separated. Like any of them can be, uh, you can have all the possible options. What I want to say, you can be, you can have clubbing of any of them. Also, that there's a possibility of all three can be in the same area. If for example, this is the case, you can have xi raised to power 5. In that case, what will happen, the partition is just 5. In that case, what has happened, lambda 1, lambda 2, and lambda 3 came to the same partition, came to the same block, right?
Mm.
So whatever you
Yes.
have as the major one, you cannot go out, you cannot expand it, you cannot have 1 1 1 1 1, you cannot have that. But what you can have, you can have the clubbing. So you can have 4 comma 1, you can have 2 comma 3, and you can have again 2 comma 3. So what I mean,
Mm.
you are allowed to have the additions. You can have two numbers in
Mm.
the same block in the next. uh, yeah, there's 8%, but yeah, I need to connect the charger, just give me a minute.
Okay.
Yes. So what? So so this is the formula exactly what we tried to say. This is exactly that formula. As you can see, you consider all the partition thing, and then you club something. You consider all the options which you can get from this, and then try to find the coefficient. So let's do that. Okay, and also you will consider the increasing thing, nu 1 greater than or equal to nu 2, and like this. Okay, so what we will do, so for us we have 2 2 1. So our lambda 1, so this is 2, this is 2, and this is 1. Okay, so
Mm.
p according to the formula, this is exactly the formula which we got from here only. So m mu, and mu is something, mu 1, and we got mu from, and there's a coefficient sum. Let's say c
Mm.
c mu. C mu M mu. Okay, like this. So let's
C
see.
mu mu or C lambda mu into M mu, ma'am.
You can. I'm not saying this is something like it's just a coefficient. So this is dependent
Okay,
on
ma'am.
this. So you can write it in this
Okay,
form
ma'am.
also. Anything. Don't.
Mm.
I hope there is. Yeah, there is some coefficient like this also. So let's say some other letter. Let's say b lambda mu. I don't want to
Okay,
confuse it
ma'am.
with some other coefficient.
Most of time we write lambda mu, cosec
Huh,
number of
right.
lambda mu.
So why we write it? Because it is dependent on lambda. It is dependent on mu.
Mm.
So that's a better
Mm.
way to write. So let's
Mm.
see. And new are coming from this after clubbing or after yeah, clubbing. Okay. So let's see how we are getting. So you have 2 to 1 right now. What you can have? Firstly, you can have 2 to 1. Other thing, there's an increasing order. So what you can have 2 plus 2, 4 comma 1. What you can have 2 plus 1, that is 3 comma 2, right? What you can have, you can have all
5
the
comma
thing.
1.
Yeah, not just 5. There is no.
No, 5 5.
Yeah.
5 5.
So you have 5. Do you have any other option?
No, ma'am.
Also you have to consider how many times you are getting, how many ways you can consider to have this value. So what I want to say, so is there any other option? No. So let's see, now let's see. So this is 2 to 1. Can you get 2 to 1 in any other option, in any other clubbing? So there is one option lambda. So you consider all three in the separate block. So that is the only
Mm.
option. So you get b lambda mu to
Mm.
be just 1. So this is
Mm.
just 1. So mu is exactly 2 to 1 plus. Now with 4 1, what is happening? So 4 1, how you are
2.
getting? You are collecting lambda 1 and lambda 2. So you are adding
Mm.
lambda 1 and lambda 2, and there is only one choice, lambda 1 plus lambda 2 comma lambda 3. Is there any other option?
Mm.
No.
Mm-hmm.
So this is
No,
again
ma'am.
1. Now let's see the other one. Next is 3 comma 2. How can you get 3 comma 2? You can club lambda 1 lambda 3. So you have clubbed
Lambda 2 and lambda 3.
lambda 1
Lambda
lambda
1
3
plus
comma
lambda
lambda
3,
3.
lambda 2 plus
Yeah,
lambda
so
3.
you have two options to get this value, right? You can either club
Yes, ma'am.
lambda 1 lambda 3 and keep lambda 2 separate, and there's another option to be add lambda 2 and lambda 3 and keep lambda 1 2 in the other block. So for this part you got two options, right? 2 into
Mm.
this.
Mm.
So you got this, and now next one is m
1.
5. Yeah, 5 is the
5,
only
all,
option.
only
You add
1.
everything. So you got this. So this is your p lambda. Is that clear?
Yes, ma'am. Yes, ma'am.
And you can see here also, this is happening exactly what we want. So you start with 2 2 and 1. Okay, so I'm just checking this two options. So what you can have, you can start with 2 here and you add this, and you keep all the
Mm.
options for the second part. Other option is you
Mm.
add this and this, and you keep this option to be separate. So you
Mm.
get all the options which we just discussed. So you get exactly this equality.
Yes, ma'am.
Okay, great. Yeah. Okay, let's move to the last question then. So this is related to, yeah, what will we get from this bijection? So this involution we have considered. So involution is mapping this the
Itself
yeah,
mapping, ma'am.
set of symmetric functions to set of symmetric functions. So, and what does this do? This sends e lambda to h lambda. Okay,
Mm.
this is the map,
Mm.
and that is enough, because if you define it for any basis and you expand it linearly, then you are done. Okay, so
Yes,
what
ma'am.
this has been done, you have just considered for e lambda, and that is a basis, because you know that E lambda is a basis for all the symmetric functions, and you expand it linearly. As you can see, this must have been written. Okay, so this has been defined for which part? Oh, oh, we came to sine. Okay. Yeah, this is cos ka. Okay. So after this only. Yeah. So this is a ring homomorphism. Omega is a ring homomorphism, and which is an involution of uh, lambda. Okay, so ring homomorphism, so it has been expanded linearly. So okay, so now that could help to find out the omega of any an sure polynomial or monomial symmetric polynomial also, because you know that if it is linear, you can expand it linearly, you can apply a new sorry, this omega to you can take it inside. What I want, you write h in terms of m, and you apply omega to it, because that is a ring homomorphism. So that is okay, right? So now in our situation, so as you can see, this is the map. So what does this do? So what will be this? Can you tell me now? E lambda will map it to
H lambda.
So you'll just get E221. And now whatever, if they ask for the coefficient of any monomial symmetric polynomial, you write h in terms of monomial symmetric polynomials, and you can get the coefficient. So uh, it's just going from one basis to another basis. And h will be what? As you know, omega square is identity, so definitely h lambda is going to E lambda, because if you apply omega again, you are getting identity, right? So h lambda must be going to E lambda, so this will be what? E221. And what about the power sum? So power sum, the formula for power sum is omega power sum is equal to this. So what we are getting for any value, so for example, if you have just p2, you'll get minus 1 raised to
Minus
power
1,
2
1
minus 1
lambda
p2.
1 values.
It's just changing the signs, considering the sign of maybe the value. So from this, so you got omega p2 is equal to minus 1 raised to power 1.
Minus P2.
It's just minus p2. And what about we need for 2 to 1? So p1 is minus 1 raised to power 1 minus 1 p1. So you'll get plus. So omega of p2 to 1 is equal to p2 into p2 into p1. So you'll get minus p2 into minus p2 into p1.
P2 square into P1.
Yeah, so you get p2 square p1, and that you can again write p2 to 1, right? So it is same. You just need to see what exactly are your numbers, and you can directly figure out, because 2 will give 1, 2 will give 1 minus, first one will give minus, second one will give minus, and third one will be just positive. So product of 2 minus is just plus. So this is the and if you need to find out for m, for the monomial symmetric function, you write monomial symmetric function in any of them, because you know for these three at least. So you write it in this form, and you apply omega, because this is linear. So this is ring homomorphism. So you can apply that, and you can get the other side, the omega of that, and in whatever way it has been asked, you can write it in this way, in that way. Okay.
Yes,
So
ma'am.
this was the last question for my talk, for the tutorial.